This also, yeah, I didn't really like they got really long, which I didn't know they did that. I noticed when I saw
Any other day.
That's your board.
Not terrific. It's exactly the time I need to.
Right, like say I'm right. Like we don't every day I have to watch, you know, instead of like hoping that you wouldn't call it that. Yeah, especially this. I was living around
on the board, I have your test topics. So we're going to continue with our test review today. And also put it up over here. So we need to be able to solve differential equations. We've been working on that on a daily basis these past couple of days. Being able to find a general and a particular solution. Or general is where your C value is still there, and then particular is when you replace your C with a numeric value. We're going to work on tangent line and linear approximation today, where we're just going to pull the order pair and the slope to build a tangent line, and then the linear approximation is where we dump in that decimal value. So topics 2 and 3 is review, but it's just getting used to pulling your slope information from your differential equation. Creating a slope field. Yeah, we'll practice some more with that. Matching slope field with differential equation. We can practice more with that. That's a lot of what you saw on your homework. The slope field homework, where you have to match the differential equation with the filled out slope field. Y equals CE to the KT word problem, where you got to solve for K, you got to solve for C. You're building all these order pairs. We did that last Friday. We can practice some more of that. Inverse trig integrals. We know there's inverse trig if there's a gap in the denominator that is 2 or more than the numerator. And if your denominator is not quite filled out with the sets of parentheses, we use completing the square to get the expressions set up so that we can pull our U and our A value. And then also quiz topics. So maybe towards the end of class, I can just go through, highlight some of those quiz topic problems. I think most of us did pretty well, but just want to highlight some of the mistakes that I saw on the quiz. And then we need to know all of our derivative and integral rules. So on your test review, I have test review packet. I have the formula sheet in the back where you can practice with all of the new derivative and integral rules that we've covered going all the way back to first semester or so. All right, let's look at number 2. And start off with part A. On the axis below, sketch the slope field for the given differential equation. So you're going to identify an order pair. So in this case, I'm going to start at the upper left corner here. I'm going to plug -1, 3 into my differential equation. This is, again, my derivative equation. -1 in for x, 3 in for y. And I'm just going to translate that number into a short line segment that's going to represent that slope. So I plug -1 in for x, I get 1. 3 minus 1 is 2. 1 times 2 is 2. So I just want to create a slope that looks like 2 on to this point. I'm just going down. And just every highlighted point, I'm identifying the location of that order pair, plugging it into my differential equation, and I'm either getting a positive number, a negative number, a 0, or undefined. Right? And if I get positive, I just do positive slope. Negative, I get negative slope. 0, I do horizontal line. And if you somehow get undefined, you probably won't get undefined here. Undefined will be like a variable in the denominator, like 4/0. Then you leave that space blank. Okay, no vertical line, just blank. Okay, so try part A. And then you can also check your progress with the next page. And then part B, see if you can answer this question after you filled out all of your slope field. And then for part C, this goes to solving the differential equation. So going back to all the process that we did, creating your fractions, cross multiplying, separating your variables. Okay. So see if you can try A, B, and C. I'll be right back. Okay, so going through and filling out all the slope information from the slope field. So identifying each of the location of the order pairs, plugging it in to differential equation, and looks like along the y-axis, we're getting everything being zero, right? Whenever x is zero, that's going to cause this entire valley to be zeroing out. So this whole entire y-axis is zero. Okay, any questions with building slope field there? Okay, okay, so part B, it says with the slope field only drawn at 15 points, it's defined at every point in the xy plane. So if we were to expand this out in all directions, there's going to be, we can see that the slope field can extend in all directions. Describe all the points in which the slopes are negative. So where's slope going to be negative? We can go to our differential equation and kind of get that information from the derivative equation. We know that there's no x value that can contribute to this overall slope being negative, right? If x is squared, that means any negative I give it is always getting me a positive number. So x won't ever contribute to this slope being negative. And then if we look at the y value, this expression can only give me negative when y is what? Wait, y has to be, what will cause this expression to be negative? Yeah, y is less than 1. Yeah, so we have two conditions for our differential equation being negative, or the slope field being negative, is when y is less than 1 and x doesn't equal to 0. Why? Because when x is 0, then this whole thing is 0, and 0 is not considered negative. So we have to write out both those conditions. Since x squared is positive, yeah, so we just have to write this out. When y is less than 1 and x doesn't equal to 0. Okay, part C, let's build our differential equation, or let's build our particular solution. So this is where we're going to need the most work here. Hopefully there's enough space for you for us to try this. It's okay, so here's our differential equation. Dy dx is equal to x squared y minus 1. And then they give us our order pair. So this will help us solve for C at the very end, right? Okay, so we'll go through our process here. Let's set up our two fractions. Let's cross multiply. And again, whenever you see a parentheses in your differential equation, it's there to help you. It's there to help separate things for you. Now, once you cross multiply and once you have your variables separated, you can then drop the parentheses, but don't try to expand. If you expand out, you lose your ability. It makes it even harder to separate your variables. Okay. All right, so try those steps and let me see how you guys do. Right, once you cross multiply, you have your dy and dx's lined up nicely. But there's one thing, well, what do you see? What's out of place? So, but if we want to move the y, we have to also move along with it, what? Yeah, the whole parentheses. So the whole set of parentheses, that means this is, yeah, this is all grouped together here. So if I want to move the y, the -1 has to come along with it. Yeah. So we divide that over. It's going to end up in the denominator. Now we have full separation of variables. Right side is pretty straightforward. That's just power rule. But the left side, we got to do a little bit of what? U substitution, but hopefully you can see that the U value is not too complicated. This should end up with just 1 over U du, ends up being a natural log problem here. But if you skip the U substitution, it's fine. Just understand that it's because there's no leftover coefficient because that y -1 is just going to produce a 1. So if you don't show your U substitution steps, it's okay. But just want to show you where these values are coming from here. So our U value is y -1, derivative is just du. It cleans up all the way to 1 over U du. And we know that 1 over U to the first power is natural log. So we go through our natural log process and then bring back our original variable y. So the left side is done and the right side is just x cubed over 3. So let me reset. So this is our antiderivative process. The integral of 1 over y -1 becomes natural log of absolute value y -1. The antiderivative of x squared is x cubed over 3 plus c. Okay, we're done with our calculus. Now we're just down to our final 2 steps, trying to solve for y and then trying to solve for c. Yeah, whenever I see natural log, I like to wait to solve for c. Just find it easier to without the natural log in the way. So raise both sides with e as the base. I can move towards solving for y first, and then I'll save for the c at the end. Remember that anytime we want to split this exponent away from the variable, we have to change that operation there. The plus, a plus or minus in the exponent is going to turn to multiplication at the base level. Sorry, e to the c. And we know this is just one giant c here. Pull that c out in front, drop the absolute value bar. The c will take in the plus and minus. Okay, so now we can, we pretty much have y by itself. So now we can worry about solving for c. Okay. 0 in for x, 3 in for y. So 0 goes in for x, 3 goes in for y. Again, careful with your zeros. We want to make sure that we're not making assumptions. Sometimes we assume that 0 is going to wipe out everything. In this case, it does wipe out the exponent, but e to the 0 is not going to be 0. E to the 0 is 1. 3 minus 1 is 2. C equals 2. Now we can go back and insert that 2 in for that C and update our general to a specific solution. Okay, any questions? All right, part D. Part D says find the equation of the tangent line at x equals 0. And then it says use it to approximate f of 0.1. We'll do this first part. Equation of tangent line, all you need is order pair and slope. And we know the x value is 0. We may have to go back to part C and grab that order pair. We do have an order pair that's at 0, 3. So we have to kind of go back to part C and grab that information. So my order pair is at 0, 3. And then the next step is we need to find the slope. And slope comes from your derivative, and your derivative is your dy dx. So I'm going to write that down here. Dy dx equals x squared y minus 1. Right? Just like how you use the differential equation to get to your slope field information. Same thing here. To find the slope, we're just going to insert that order pair into our derivative. It's like f prime of 0, but the derivative just looks a little more complicated, but it does the same thing. It gives you slope. So 0 in for x, 3 in for y. We get 0 times 2, which is 0. So my slope is 0. Okay. Let's build our tangent line equation. So y minus y sub 1 is equal to m times x minus x sub 1. So y minus 3 is equal to 0 times x minus 0. Now, my equation is just going to be y equals 3, but I just want to kind of leave it in this form because I want to show you what would be like if we were to do linear approximation. So linear approximation at f of 0.1. So normally, your tangent line equation may not give you a slope 0. If it doesn't give you slope 0, then you'll end up with a decimal value. So linear approximation just means you're going to plug that 0.1 in for x. I know right now it doesn't make any difference because this thing is just going to leave us with 3, but just want to show you that process. So if this slope wasn't 0, you would just enter that in for x and get whatever decimal value that comes out of it. In this case, there's no decimal value because that 0 will wipe everything out, and I'm still left with just 3. But hopefully this is review from first semester, right? Tangent line equation, find your slope, find your order pair, plug in tangent line equation, just plug that decimal value into your tangent line equation, and whatever decimal you get, whatever number you get is your approximation. Okay, before we move on, I just want to point out something that students mix things up with, especially when these problems are next to each other. Okay, solving a differential equation is not the same thing as finding the tangent line. They both use the differential equation, but they use them differently. Okay, solving differential equation is going to be a lot more involved because you got to go through a whole process of building that equation up from the derivative. But tangent lines should feel a lot easier, right? You're not messing with the differential equation. All you're doing is plugging in to get the slope, get the order pair. At worst, you're going to get your order pair from part C or from this part of the problem, and then finding your tangent line, plugging in, and getting your decimal value. So on the test, I would see students, they would start doing all this work trying to separate the variables. But when you're finding tangent line equation, all you're doing is finding order pair and slope. You're not messing with this equation. But when it says solve a differential equation, that means they want you to get this derivative up to the function level. But tangent line, all we want is order pair and slope. We just want to build a tangent line. We're not trying to solve this equation. So that's one big mistake that students make on the test. I just want to make sure that you guys can see that distinction and that those processes are clear for you. Okay, let's go to the next page. Okay, I'll save number 3 for later. Let's try 4 through 7. So these are mixture of some quiz review as well as some problems that involve a newer process involving arc trig. So let's look at number 4. Okay, how do we know that this problem is not just a typical U substitution problem? What gives it away that this is a special process? What do we talk about? What do we say about the exponents that tell us that this is a different process here? This degree is what? Versus this degree? Yeah, not only bigger, but that gap is what? 2 or more, right? So if the gap is 2 or more, that means that your normal U substitution is not going to end up canceling out, right? If my U value is 1 minus x to the 6th, my derivative will turn into x to the 5th, and that x to the 5th won't match up and pair up with that x squared. So anytime we see a gap of 2 or more with the denominator being greater, again, we ignore that square root. Just look at the exponent. We know that it's got to be an arc trig in order to shrink that exponent down a little bit more. Okay, so we see a square root, so we know it can't be arctangent, and we have the constant followed by the variable. This will probably be the best fit with arc sine. So let me write that arc sine rule, which we're going to have to work on memorizing. Arc sine is the only one without the 1 over a coefficient. It just jumps directly into arc sine. That's u over a plus c. Right. We know that if we want to use an arc trig, we want to get the denominator to show a set of parentheses. So we have to adapt this equation into the parentheses without changing the overall value of the expression. So 1, though, is easy because 1 squared is the same thing as 1. So 1 is the only time when we can bring the exact value down. But for x to the 6th, what can I put in here so that if I square it, I'm not changing the overall value? X to what power? Third, yeah. So 3 times 2 is 6. So now what we see inside the parentheses are our A and our U value. Again, that we can tell the difference because A is the constant, just numbers, and variable, and the U has the variable in it. So A is 1, U is x cubed, derivative is 3x squared. Okay. Now we're going to make our substitution here. Our goal is to make our problem look exactly like the rule that we want to pull, that we want to use. And then we may have some coefficients in front, but it should look exactly like the rule that we want to use, and then we can apply that rule. X squared cancels out. We can pull the 3 out as 1/3. Now, if we look, we have a perfect match with our rule, just with that coefficient in front. And now we can apply our rule. There is no 1/a, but we do have a 1/3 that we need to include in our answer. So 1/3 arc sine. And now let's bring back our original problem here. Our U value is x cubed. Our A is 1. All right, number 5. So if we look at this setup here, there's a gap, degree 2 versus degree 0. This is not just going to be a normal use substitution problem. This is going to be an arc trig problem. We know it's arctangent because there's no square roots, but also we know that the denominator is not quite set up for our a squared and u squared. We got to go through completing the square. Anytime we see a trinomial, we have to work on getting that variable into a binomial squared. So we'll step to the side and set that up. So the way we set it up is we're going to add a space or have spaces on both sides of your constant. Don't change the constant, but you're just going to add a plus space and a minus space. It's always going to be a positive number followed by a negative number. Whatever number that we find to factor this trinomial, we're going to make sure we subtract it so we don't change the overall value of my expression. Okay. So my formula is b over 2 squared. My b value is the number, the coefficient in front of my second number, my second term. So my b value is -6. -6 over 2. We're always going to get a positive number because we're always squaring it. So +9 and then -9. So the whole point is this should allow this trinomial to factor nicely. Okay? Well, multiplies 9 and adds it to be -6. negative, what? -3, -3, right? Okay, so we can merge that together. We always are going to get duplicate binomials, which we can merge together. And then plus 14 minus 9 is 7. Sorry, 5. And I can put 5 inside a set of parentheses as what? Can I put inside without changing the overall value of 5? Make it root 5, yep. Yeah, let me rewrite the problem here. Okay, now we're we have a much easier time pulling our A and U value. Again, for arctangent, your A and U value may be flip-flopped because they're being added, so it doesn't matter which one comes first, but the way that you can tell is your A is the number and your U is the variable, or has the variable in it. du dx is 1, so no leftover coefficients. Okay, not square root. Thank you.
Stay here. You can say food.
You can. Okay, so the rule for arctangents, I'll write that out here. We also need to commit this to memory, which is 1 over A arctangent U over A plus C. So the -4 has to stay in our answer. So I'm going to bring down -4 first. And then the 1 over A, so 1 over root 5. And then arctangent, and then U over A, so U over A. Plus C. All right, number 6. Six and 7 are like quiz review problems. Now we see that big 9 there, 9 raised to the exponent. This should remind us of a to the u. But if we want to do a to the u rule, that a needs to be in the numerator. So here's the rule that we're trying to match. So if I want that 9 to be the numerator, I got to force that exponent to be negative so I can push that up. So let's rewrite this problem before we go through our full use substitution. This is a better form for our problem here. So this should really be the starting point of our problem. Our a value is 9. Our u value is the entire exponent. Now we can begin the process, and the hope is that this derivative will handle this mess. Hopefully this will cancel out down the road. Let's go through u substitution. So to underline what I want to focus on here. Replacing the exponent with the u, and then down the road we can replace the dx in terms of u. So this is one of our original derivative rules here. Cosecant of u is negative cosecant u, cotangent u times u prime. Now, cosecant will produce its own negative, so the two negatives will cancel out. Cross multiply. Make our substitution, 9 to the u times negative cosecant 2x. This is from the original problem. And then the dx has that match that we can pull. All right, we have a good match here. Cosecant, cotangent all goes away. There's a negative 2 that's going to remain. I think my key is a little bit off here, but the negative doesn't cancel out, and the 2 doesn't cancel out either, so that needs to stay. Oh, I want to point out something that I see all students do on the quiz is merge this to be negative 18. Okay, why can we not make this negative 18 to the u? We have 2 times 9, so why can't I just make that 18? Anybody see any issues with that? So 2 is a constant, but is 9 a constant? Right, not 9 is a exponential function, so these are not compatible. So that means now if it was 2 to the u, then maybe that's a different story. But right now, the 2 and 9 are not in the same family, so we can't just merge them together. So we kind of have to leave them separated. Okay, so now we're ready to jump into our integral rule. Negative 2 first, and then we follow our rule, 1 over natural log of a, so 1 over natural log of 9. And then times 9 to the u, a to the u plus c. And our final step, just bring back our x variable. If you want to merge this into one fraction, you can, but if you didn't, it's fine as well. I think I have the key showing a positive sign in front, but it should be negative. Okay, last one here. Let's try number 7. This is one of our newer integral rules. Secant involves natural log. So let me write that rule, see if you guys can try it. Okay, go through your substitution. There is going to be some leftover we got to keep track of here. For homework, I'd like for us to go back to the Unit 7 homework packet. We have one set of pages that we haven't quite done yet, so if you can just do page 7. So just page 7. Okay, I'll send out a reminder this afternoon. Come get your phones. And we have another full day, full class period tomorrow to do test review. And then Wednesday, half day, and then half period, and then Thursday, half our test. Yeah. How to get that negative two? My U value. My U value was negative cosecant. The problem originally had a negative, right? So my U value is negative cosecant U. My derivative is negative, so the two negatives cancel. Because cosecant's derivative is just negative cosecant tangent U. So there's two negatives, so that so then I put that back in here. And then everything canceled out, but the negative from the original problem doesn't go away. So I need to hold on to that negative. Oh, sorry, it should be a negative. Is that what you were thinking? That too should have been.
What?
Yeah, it should be good.
Also, you can't,
Yeah. Yeah, because -2, imagine like -2 times 3 to the x. These are not compatible. I cannot make this -6 to the x. The only time these are compatible is if they share the x. If they share the x one, then maybe I could have this -2 times then this. But yeah, that's my mistake. It should be a negative. It should be negative 1/2.
So it was. Yeah, boy, so. 320. No, that was 400.
That's why.